Hello, everyone, and thank you for joining this session. I'm Nina Sadiki, founder of Erode Power Consulting. I've joined forces with ETAP Dynamic Department Jose Macias to bring you this presentation focusing on impacts of field-measured unbalanced harmonics for EV fleet charging on equipment for power distribution and supply and from a reliability standpoint. So here we focus on why power quality matters, what causes harmonics in EV, and then we mentioned how we went about field evaluation, what field issues we saw, and then what are mitigation techniques. And then from there, I will pass on the presentation to Jose so he can talk about the ETAP case study. So why is power quality important? Power quality is the silent threat to your operation, and it is costing you money. It impacts equipment reliability. It impacts equipment lifespan. It impacts operation efficiency and energy cost as well. And then, of course, if you're not complying with the standard, then there will be penalties for that as well. So what causes harmonics in AV fleet? It's power electronic converters, rectifiers and inverters converting AC to DC or vice versa, switching operations, rapid switching of transistors, charging or fast charging methods and patterns of charging, and then, of course, whenever we have one charger, the system reacts completely different than we have a fleet charging, which is charging 300, 500 milliamps simultaneously. And how that impacts the system is very different than what we're seeing in the lab or it's shown on the cut sheets. So harmonic in L3 chargers, the distortion of the waves show very differently per phase on an L3 charger, which is a three-phase charger. And then on the L2 chargers that are single phase, we also noticed imbalances in the system. So how did we go about planning this field evaluation? We went collected data at multiple points for an agreed upon duration. So 4 to 6 weeks at each site, and then at the common point of coupling, at the switchgear, at the panel level. And we brought that into ETAP model, which Jose will explain a little bit more. And then from there, we put together root cause analysis, a comprehensive report that also focused on compliance review, and then developed an action plan, then installed some mitigation solutions, and then further evaluated our field results. And what we noticed is that we increased energy savings by 10% and then increased uptime by 20% in the fleet. So then we took that feedback back to design, standardize, and modularize the design on the AV fleet. So field observation, whenever we have harmonics, it's going to be heat losses on transformers and conductors, which then leads into energy losses. Then there's going to be stress on the insulation of equipment, which then reduces the life cycle of the equipment and the lifespan of it. And then there's definitely always nuisance tripping with relays, saturation of CTs that then cause equipment to misoperate, breakers and fuses as well. So design considerations, of course, grounding and bounding is very important, and ensuring that we perform harmonic early on in design so we can mitigate the design considerations we need and incorporate them in there. K-rated transformer is a good design solution, which really can withstand harmonics, but it's not mitigating. It's manufactured with oversized neutral conductors. It does nothing for mitigating the system, but it's built to handle the stress imposed by harmonics. Another mitigation technique is passive filters. They do absorb and divert harmonics, but a very specific frequency that we specified for it. And it's a lower cost and a lower footprint. It is connected in parallel with the load. Active filters are other solutions. These are system-level solutions that inject equal and opposite harmonics. They're much more flexible and target multiple frequencies. They compensate reactive power and corrective power factor as well. The downside of that is these are expensive and they do need a larger footprint. Another harmonic mitigating technique is transformers. Mitigating transformers are low maintenance, low cost, and they are superior to K-rated transformers, and they do absorb harmonics. They always stay energized and they are reliable. But to be able to accurately determine the required technique, we have to perform an unbalanced harmonic analysis. And I will pass on the presentation to Jose from ETAP Dynamics Department to explain how. Thank you.
Hello everyone. Jose Macias is unavailable at this time due to some personal emergency. I'm Deepika Tumala from ETAP's Dynamics Division. I'll walk you through the process of harmonic evaluation in ETAP for the case Nina presented. Thank you, Nina, for sharing your expertise and providing an insightful overview of harmonic evaluation and the issues observed with EV chargers in the field. And now it's time to switch to ETAP to look at a few more details of the actual case, data requirements, project setup, analysis, and the results. Let's switch to ETAP. As part of our engineering services, our team at ETAP Dynamics Division performed unbalanced harmonic analysis study for a client. The project included multiple sites with electric vehicle charging stations that had level 3, that is DC fast chargers, and level 2 chargers inside these panels here were installed. The objective was to assess the overall system response due to harmonic distortion introduced by the EV chargers installed in the sites, and to determine system configurations and conditions that cause voltage or current harmonic distortion to exceed the limits established by industry standards such as IEEE 519/2022. Once all the available data was received from the client in the form of electrical permit drawings, equipment data sheets from the manufacturers, panel schedules showing different charger configurations of level 2 and level 3 chargers, field measured data of harmonic distortion with the PQ meters that were installed in the field, and equipment photos and reports from other system studies. We started developing ETAP digital twin models of each of those sites. So the one that we're seeing right now is a replica of digital twin models of one of those EV charging sites that were analyzed. So if you notice the topology of the system here, so it's represented by utility that's feeding to medium voltage switch gears, and the switch gears are feeding the switch boards through utility service transformers. And each of those switch boards have these panels with level 2 chargers and level 3 chargers connected. If we go inside the panel here, we could see the charger configurations, the connections of chargers on different phases. And this is a level 2 charger inside ETAP, which is modeled using the charger element, the single phase charger element. If we go out of this composite and look at this DCFC charger, DC fast charger, which is level 3 or L3 charger, we're modeling it using the static load element, so we could model the unbalanced harmonic spectrum, modeling it as an unbalanced harmonic source. While the one-line diagram was being created, we also worked with field-recorded harmonic distortion data for creating harmonic libraries. These libraries were created considering the 95th percentile of the recorded data to use in the modeling of harmonic sources. In case of L3 chargers, the current drawn by the equipment during the charging cycle has a dynamic behavior. The harmonic current injection from this equipment to the grid is also different depending upon the moment in time during the charging period. In order to account for this behavior, two sets of harmonic data have been extracted at two different instances in the charging cycle. One at the beginning of the cycle, where the charger is constantly drawing its rated current, considered to be the highly loaded condition, Another one when the charger current consumption has decreased towards the end of the charging cycle. It was considered to be the lightly loaded condition. And we can see these libraries going to the references tab, library, going to unbalanced Siemens. We would see two sets of data created for L3 charger, highly loaded and lightly loaded conditions. Several scenarios were created to perform simulations to determine system responses under various possible operating conditions, including the effects of unbalanced loading and system configurations. 6 PCC locations, point of common coupling locations, were analyzed to evaluate the harmonic distortion levels coming from the EV charging facilities towards the utility network. So these locations have been highlighted with ellipses around. So let's take a look at one of those buses. One is the utility bus feeding the medium voltage switchgears. If we go to the harmonic page, we'd see it set up as PCC/POI with the rulebook set up to compare the harmonic distortion results with the limits from this rulebook. We have 5 substation composites here. Going into each one of them, we'll have the service entrance transformer. Secondary of each of those transformers are the locations where the results were analyzed. Let's take a quick look at the harmonics page of one of these buses, set up to PCC/POI with the rulebook set up to compare the distortion results of bus voltage distortion results against the voltage limits from this rulebook and the current distortion limits at the connected branch to the current distortion limit set up in that rulebook. So now with this available information, let's try to run the scenarios. We have one of those scenarios where harmonic voltage or current distortions are exceeding the limits provided in the standard. So the one that we're going for right now is scenario 5 BC 100% load, where we could see exceeding distortions in substation feeder 4. So before running the study, let's move out of this composite and move into substation feeder 4. And we're evaluating the results at this transformer secondary bus and service entrance cable here. So let me go and run the scenario. Let's look at the voltage distortion results at this bus and the current distortion results at this branch service entrance cable. Let's go to alert view. If you notice, we have several alerts for cable LVSB4 for different harmonic orders, including the one for total harmonic distortion, showing limits of 4.75% for current distortion, whereas phase B has 4.92%, it's exceeding the limits provided in the standard and study case settings. So let's plot this to see how distorted the waveform is. Cable LVSB4 phase B. So it's a distorted waveform. Now let's also run the case where we have a passive filter sized for the 5th harmonic order. So this is one of the solutions provided to the client for addressing the harmonic distortion issues noticed in the field due to the harmonic content from the EV chargers. So now we have the results for this scenario. Voltage distortions at this bus have reduced, and the current distortion on phase B for this cable also has come down from 4.92 to 3.56%. Let's take a look at the plot. Let's do it for the order. If you notice, the waveform distortion has reduced significantly. This was the one without the passive filter setup, and the one above is the one with the passive filter in the system. So let's minimize these and now run another scenario with active harmonic filter. So if you notice, there's results here from this case with active harmonic filter installed. The voltage distortions at this bus got mitigated significantly, and the current distortions have been reduced significantly as well. So let us generate this plot for this cable LVSB4, and let's compare it with the case where we had distortion before. That is the case with 100% load and no filter installed. So the waveform got cleaned significantly with the active harmonic filter in place. So as part of this harmonic evaluation, we noticed violations of percentage total current harmonic distortions at this PCC location. To address the issue, we have run scenarios that were set up with active harmonic filter or with passive harmonic filter installations in the location. In both cases, we've noticed significantly reduced distortion in the waveform. Similar to this PCC location, there are other locations in the systems and in all different sites. For all the scenarios that were set up, among them, several of them had PCC locations where either voltage or total current harmonic distortion violations were noticed. And for all those cases, similar solutions were recommended to the client for mitigating the effect of harmonics and the distortions well within the limits provided by the standard. With that said, let me take you to the transformer K-factor calculation that was also performed as part of this analysis in the project, and recommendations were provided to the client in terms of K ratings of the transformer. So measurement of harmonic currents in the network and determining the heating effect of these non-sinusoidal currents on the transformers is an important step in determining appropriate transformer size and K rating. So K factor of the load harmonic currents is calculated in ETAP to determine the required K rating of the transformers feeding the nonlinear loads. In this case, for this transformer, calculated K factor is well within the rating of the transformer, but there are several other locations for the transformers connected to the panels where chargers are connected, such as this one, where calculated K factor due to the harmonic content is higher than the K rating of the transformer. Such cases might lead to excessive heat losses within the transformer, which would reduce the equipment operating life eventually. So for such scenarios, we have these evaluations done and recommendations offered to the client. And in such cases, if clients were to choose higher K-rated transformers, there is a feature to choose the K rating of the transformer here and perform evaluation with a different scenario in such case. So as part of this analysis, in addition to calculating the K factor due to the harmonic composition and the load current, ETAP also identifies the derating requirements of the transformers and flags them in the alert view. So when a transformer is subjected to a load current having significant harmonic content, additional eddy current losses in the winding and also in the metal parts of the transformer elevate the temperature of those parts above their normal operating temperature, leading to the loss of life expectancy of the transformer. And to avoid such scenarios, ETAP calculates the derating factor for load currents and flags derating alerts for both primary and secondary windings of the transformer. So let's take a look at the alert view in this case. Transformer LVSB4 panel 7 and transformer LVSB4 panel 6 are both flagged for derating condition. If we open one of the transformer editors and go to the harmonic page, we see the rated ampacities of the windings of this transformer are given here. But capacity ratings that we see under ratings in the alert view are lower than this. So these are calculated using the derating factor, and currents passing through the transformer are compared against the derated values, and derating requirements are flagged in the alert view for the devices with the condition overload with losses. So some transformers were found to have continuous overload due to the effect of harmonic distortion. So alerts, as we're seeing, are generated based on the derating factor calculated from the harmonic content in the current injections. So to sum it all up about this case, all the EV charging sites that were considered for analysis were modeled in ETAP using ETAP digital twins. And for all those sites, several scenarios were created considering all possible conditions and configurations to perform the analysis. Libraries were created by extracting the data from dynamic charging cycles of the DC fast chargers. And the evaluation was performed to identify percentage total current and voltage harmonic distortions at the point of common coupling and other locations. And those locations where the results were exceeding the limits were identified. And possible solutions such as installation of active harmonic filters at the switchboard level was recommended to deal with the excessive voltage distortion that was noticed in some locations. And additional characteristics of this technology, such as power factor correction, phase load balancing, and dynamic harmonic mitigation adjustment, match with the operating requirements for the client systems were also recommended. And based on the common findings for all the sites, it was recommended that for future sites, K-rated transformers are installed for the panel. So as observed generally for all the sites in the study, further loading could create unbalanced conditions and introduced additional harmonic distortion to the system. So having these K-rated transformers and having these filtering devices in place could take care of harmonic distortions due to unbalance created with the additional loading in the system in future. So with that said, we're wrapping this session up. Thank you all for joining us today.